Hello friends, I welcome you all to this session on power plant engineering. So the topic of the day is regenerative feed water heating. Now when we say regenerative, that means we are trying to heat the feed water not from the external source. That means we are not heating it, uh, uh, this portion of water in the furnace itself, but we are doing what we are internally heating it, such that what we are doing is we are taking the steam from the turbine and then heating the feed water, so it becomes internal. And due to this, what will happen, efficiency is a definite guarantee of efficiency rise. And what implications are there apart from this, we'll see once we study it. So here, now let us say I'm having a boiler, then the turbine, and then the condenser, then pump. Now in previous cases, what you have observed that from pump directly we transfer it to boiler, means economizer and boiler. Okay, but now what we do is we don't directly transfer this water to boiler. Instead we transfer it to a heater, that is feed water heater. Here what happens, water comes and it directly mixes with steam which has been bleeded or extracted from the turbine, and there will be direct spray of that particular steam into the water, feed water heater, or the feed water which is entering. Let us do what, let us take this color, maybe this will work. Okay, this is not working, doesn't matter. So let us say that this is the water. Now feed water directly comes, mixes here, and what happens due to mixing? Due to mixing, the temperature of feed water will rise. There is a direct contact of bleeded steam from the turbine with this water. This is the reason why this particular feed water heater is also called as direct contact feed water heater. And then you are having another pump, because the sole purpose of this direct contact feed water heater is not only to increase the temperature of water before it enters into the boiler, but at the same time remove the dissolved gases. As you know that with the increase in temperature, the solubility of the gases reduces, so this will result in reduction in the solubility of water and solubility of gases in the water, and then you will be having vents here, due to which those gases can be taken away. So dissolved gases can be taken away. Now once this has been done, so due to this, what will happen, there is a reduction in pressure, drop in pressure. So one more pump is required to perform this particular task. Okay, let's say not only I am having one feed water heater, let's say I am having two feed water heater. So again I will be having one more this feed water heater, let's say, and I am extracting the steam from the turbine on the higher side, that means higher pressure side for this. So this again getting mixed. Okay, and this comes, this mixing happens, and then again we have to have one pump, because again the same vents will be there to remove the gases, and this hole will then be fed to the boiler. So if the state is 1 here at the exit of boiler or at the entry of turbine, let's say it is 2, and this state is, let's say, 3, this is 4, and then this is 5, and then this is 6, then 7, then after pump, let's say it is 8, and then after mixing, let's say it is 9, and then this, let's say, is 10. So these many processes are there. Okay, for the time being I am assuming that 1 kilogram of steam enters into the turbine, then out of it m1 kilogram is bleeded for this feed water heater. Let's say it is feed water heater number 1, and this is feed water heater number 2, and m2 is coming to the feed water heater number 2. Now out of 1 kilogram, if m1 I have taken here, m2 here, then how much will be coming to the condenser? It is m1 minus m2, and then this 1 minus m1 minus m2 will come here, m2 get mixed, and what is the amount of steam left here? It is this 1 minus m1, and this m1 minus m1 will go to this feed water heater number 2, and this m1 will mixed with it. So what is the amount of water which is moving to the boiler? 1 kilogram. So this completes your mass conservation, mass balance. Now comes the thermodynamics of it. So before we have to do some we have to draw the TS diagram. So let's say that this is the TS diagram for the situation. So this is the boiler pressure, and say that this is the condenser pressure. Now this is the point at which the steam enters into the turbine. Look here, this is the one. Then total expansion will be from 1 to 4. Okay, let's say everything is isentropic, no problem. Then this is your isentropic expansion from 1 to 4. Now in between you are having two extractions from 1 to 4. One is at some pressure, higher pressure, and this is at lower pressure extraction. So 2 and 3. So let's say this is your point number 2 and this is your point number 3. Doesn't matter. The points 1 and 2 will be depending on the design of the boiler, design of the turbine, and as well as how much efficiency you want, or this is basically the design aspect. We are just roughly trying to understand here. Now 4, it comes to 5 after condensation. Okay, from 5 there is a pump 5 to which increases the pressure up to 6, which is nothing but the pressure at point 6 will be nothing but the same as this particular extracted steam pressure, or so that extracted steam pressure is slightly, in principle it should be slightly more, but for the sake of simplicity we say that this pressure has to be same as this pressure. So what happens at point number 3, we are extracting. So let's say this is the extracted steam. Now what happens, the one which is coming from 3 and the one which is coming from 6, they are getting mixed and creating a state 7, and I am assuming the 7th state to be saturation state. So 5 and then to 6, let's say this is 6, and then this is your point number 7. How much has come? M2 has come from here. Now what about point number 3? So if you look, point number 3, this is point number 3 itself. What about point number 2? So this is 2. Now there is a pumping from 7 to 8. Okay, there is a pumping from 7 to 8, slight pumping, and before that we have to draw this particular also. Now this is the pumping from 7 to 8, and then the state after mixing, from 2 it is coming, from 8 it is coming, the state is 9. Okay, so this state is 9. Then from 9 there is another pump which is increasing the pressure to point number 10. So this completes your Rankine cycle for the problem. That is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. And here two extractions are there, M1 in the higher pressure side and M2 from the lower pressure side. Now what you have to be very cautious is 1 kilogram enters. So here from 1 to 2 the amount will be nothing but 1 kilogram. So as M1 has left, so what is the amount now? It is 1 minus M1. As M2 also left, so what is the amount? It is 1 minus M1 minus M2. So this 1 minus M1 minus M2 will be getting condensed inside the condenser and releasing the heat, that is Q2. Then there is a pump work, and then this 1 minus M1 minus M2 is directly getting mixed with M2. So what is the amount which is now transferring? So what is the mass going here? So it is 1 minus M1. So this 1 minus M1 when mixed with M1 will become 1 only. So in this way your mass balance happens. Now comes the amount of energy interaction for different things. So what is the work output and so on. So if you look, the work output from the turbine, that is equal to, you cannot write now H1 minus H4. Why? Because there is continuous reduction in the masses. So for 1 to 2, it is 1 times H1 minus H2 because 1 kilogram was expanding. Then from 2 to 3, the mass is reduced to 1 minus M1. So 1 minus M1 H2 minus H3. Then from 3 to 4, the mass is now 1 minus M1 minus M2 H3 minus H4. So this is the turbine work. Now if you slightly solve this equation, what you will be getting is H1 minus H2 minus H2 plus H2 minus H3. So this is your minus M1 H2 minus H3, okay, and then plus H3 minus H4, and then what, minus M1 plus M2 H3 minus H4. Now if you solve this, this will get cancelled out, this will also get cancelled out, and you will be getting H1 minus H4 minus M1 H2 minus H3 minus M1 plus M2 H3 minus H4. So now this is something which you have to understand. If there would have not been any extraction, M1 and M2 are not there, then the total expansion work will be H1 minus H4. This is the one. But due to extraction of M1 and M2, what has happened is there has been a reduction, or this particular amount we are subtracting from H1 minus H2. So what happens, you can understand that the first thing is due to regeneration or due to extraction, what has happened? The turbine work output reduces. This you should understand. So the first thing is, due to regeneration, the work output of the turbine reduces. Okay, now this is all. Now comes the pump work. What is the pump work? It is first, this is the CEP, that is the condensate extraction pump. This is CEP. And here, these are what? These are nothing but, these are feed pumps basically. They are called as boiler feed pumps. This is BFP1, or let's say BFP2, and this is BFP1. So two pumps are there. So now, if you try to solve for the work output, you can say the work output of CEP plus the work required in CEP plus BFP2 plus work required in BFP1. Now for CEP, if you look only the magnitude, it is what? It is H6 minus H5. But what is the mass? It is 1 minus M1 minus M2. So 1 minus M1 minus M2 H6 minus H5 for CEP, for this one. For BFP2, it is now 1 minus M1. So it is 1 minus M1 H8 minus H7. So 1 minus M1 H8 minus H7. Now comes BFP1. So now this M1 has merged with this, so the mass is 1 only. So it is H10 minus H9. So this is pump work. Now you can also see that we have to, for these open feed water heater or direct contact, they are also nothing but open feed water heaters. They are also called as open feed water heater. So for these open feed water heaters, you have, for every open feed water heater, you have to supply, or you have to install one pump. So there the cost of work will be more now. So the another implication of this is the first one. Now the second thing which you can observe is that due to regeneration, due to regeneration, what the pump work has also increased slightly. Why I am saying slightly? Because in comparison to the turbine work, the magnitude of pump work is very small. So if if the pump, as the pump is handling the liquid, so the pump work will increase slightly, but not very high, not that much what the turbine work was actually producing. So if you look the real case, you will be when we draw this particular cycle in the example, you will see there is a slight slight amount of increase in the work. We'll see it, okay, but there is an increase, okay. Now, what about the heat loss? So let us discuss about this. So the heat loss Q2 will be what? This is nothing but the energy lost here, that is H4 minus H5. Is it really H4 minus H5? No, because the mass is 1 minus M1 minus M2. So it is 1 minus M1 minus M2 H4 minus H5. So now if you solve this slightly, you will be getting H4 minus H5 minus M1 plus M2 H4 minus H5. Now you can very well appreciate the fact that due to the presence of this regenerator, if there would have not been any regenerator, so this is the heat loss. But due to regenerator, we have done what? We have reduced this much amount of heat loss. Why? Because the condenser has to handle now lower mass. So lower mass means lower heat loss. And as the condenser has to handle lower mass, so what has happened? Yes, you have guessed it right. So as the condenser is handling lower mass, so due to regeneration, the size of the condenser reduces. So it decreases. So size of the condenser decreases due to regeneration as the condenser has to handle lower mass for the same amount of work output. Okay, now what about the boiler? So heat we are adding in the boiler. Okay, so where is it? So we are adding the heat. If you look the schematic from 10 to 1, so this is what looks in your Rankine cycle. So it is H1 minus H10 as only 1 kilogram of steam is being handled. So it is 1 times H1 minus H10. Now you can see that if we would have not supplied, if we would have not used these feed water heaters, then what might have happened? We have to supply energy from somewhere here till this point, and this is a huge amount of energy transfer. So externally we have reduced that exergy, externally we have reduced that loss. We are now transferring from 10 to 1, not from here to here, and due to this there is a increase in the mean temperature of heat addition. So you can think in this way: if we would have to supply steam supply energy from, let's say, some 200 to, let's say, without regenerator we have to supply from 200 to, let's say, 550, and because of regenerator now we are doing the same thing from 350 to 550. So due to this, what will happen here? The mean temperature will be higher. So if you roughly try to find out the mean also, so that is higher in comparison to this. So what happens due to this? The mean temperature due to regeneration increases. And I have shown you in the previous lectures that as the mean temperature increases, so that will result in what? That will result in increase in the cycle efficiency. And hence, due to regeneration, cycle efficiency, which cycle? Rankine cycle. Rankine cycle efficiency increases, and hence the regeneration always result in increase in the Rankine cycle efficiency. And the inverse of Rankine cycle or inverse of efficiency is the heat rate. So heat rate is what we say as nothing but inverse of efficiency. So as efficiency increases, so what will happen to heat rate? Heat rate reduces. Heat rate is nothing but the amount of heat which you supply in the boiler for unit shaft output. So that heat rate reduces and hence the plant efficiency improves. So these are some of the points which you have to understand for this regenerative feed water heating, and that is all the thermodynamics of it. But apart from this, there is one more thing, very important, that work output or the net work output will reduce. So due to regeneration, for the same work output, when I say same work output means without regeneration, for the same work output. Now look, work output reduces due to regeneration, but if I want the work output to remain the same, then what I have to do? Then I have to increase this 1 from 1 plus m1 plus m2. And who is capable of increasing the work? Who is responsible for increasing the steam generator, that is the boiler. So as the work output reduces, so if I want the same work output and also install the regenerators, then what I have to do? I have to supply more steam. Okay, so for the same work output, more steam has to be supplied. More steam has to be supplied. That is bigger boiler. So to increase the efficiency, now you have to do so many things. Why? Because if you install a regenerator, what happens? First, work output from the turbine reduces. Pump work input slightly increases. Heat rejection, yes, reduces. Heat input, yes, reduces. But at the same time, for the same work output, you have to supply more steam. So bigger boilers. Bigger boiler means more revenue, more investment you have to do. So there are so many things which you have to understand when it comes to regenerative feed water heating. But very important, apart from this, if you look very closely, friends, this analysis cannot be done until or unless you know what are the extractions. So how to find out these extractions? So to understand how these extractions are evaluated, what we'll be doing is we will be creating a control volume around these feed water heaters. So first let us do what? Let us try to analyze this particular feed water heater.